the overview of the tremendous amount of work that has already been done in the last decade, basically. First works in 2015. And now we're really seeing a resurgence of works that leverage videos and that get really good representations. And I'm going to highlight and go into a bit more detail on two works that we've published very recently. In case you were there at my talk yesterday, there's quite a bit of overlap with that talk, but I assume you're here because you weren't there yesterday, so that's great. All right, not going to repeat myself too much. We've seen these points already introduced by Mohammed Reza about why we should care about self-supervised learning. And self-supervised learning allows us to go towards this massive scale, use new data sets, really interesting data sets that don't require human labels, that don't require being class balanced, etc. But here we are, for the most part, self-supervised learning on ImageNet, and everyone does self-supervised learning on ImageNet. It's really a bit frustrating, especially if you look at self-supervised learning principles and you just compare them one by one with ImageNet, right? You have self-supervised learning. It should scale to billions of images, and it does. Doesn't need curation, can learn generic representations, and shouldn't require much hacking or customization. Yet the status quo on ImageNet is that labeling still remains expensive, and it doesn't really scale. There's inter-rater agreement is tricky. It's not clear what labels to even use. It's still an object-centric data set, and the tuning of augmentations, learning rates, everything is just tailored towards ImageNet. So we're really overfitting on ImageNet, even though we're not even in the domain of using supervised labels. So there's really no reason to use self-supervised learning on ImageNet. So why are we doing this? Well, I think one of the reasons I've used ImageNet is also that it's simply protocol. Another reason that you will also hear is that it does work relatively well, which isn't really a good reason. If anything, it should be the opposite. Like if it doesn't work well, then we should find out why it doesn't work well. So yeah, I think we really need to break free from ImageNet. And I mean, as the title of the tutorial suggests, we should also break free from images themselves. One side note here, as one remedy already for breaking away from ImageNet, there's one data set we proposed in 2021 already, which is called PASS, which is basically the unlabeled variant of ImageNet in a way. So it's GDPR conform. It doesn't contain any pictures of humans. It's completely random images. So you really have this this long tail of classes. You don't have any class curation. You don't have any fine-grained categories unless they naturally appear in this random amount of images. And it should really be a better indicator of how well your image representations can learn on random images compared to ImageNet, which is very curated, just as a side note. But really, we're here for videos. So we know that humans don't learn from images like this, right? I don't know about you, but when I was a baby, I didn't look at all the ImageNet images in like rapid succession, and then suddenly I developed my visual acuity and could run on a straight line or something. But rather, it looked a bit more like this, at least on the left side for me, that is. Or maybe you wrote a dog, but so I mean, there's a huge difference on how the data differs, right? Like there's crazy amount of correlation between the frames, there's continuity, there's object motions, there's geometry happening. There's a lot of things happening. So this is really the data that we know works. So we should really figure out how to make it work for AI as well. And especially for us, for everyone here that's keen on doing research, this presents a huge opportunity because current vision foundation models, they're all trained on images for the most part. Now is really the time to start working with videos and really be at the frontier of building these new vision foundation models that will all be built from videos in the next couple of years, I'm pretty sure. Why I'm sure? It's pretty much the scale argument at this point, because if you look at the amount of data that exists in videos, it's sheer incomparable to the amount of images that you have. There's tremendous amount of content being created, being uploaded on Instagram, on TikTok, on Netflix, everything. YouTube, of course, still growing in crazy amounts. And all of this data we can leverage, but we need the right techniques to do that. And I will introduce two techniques today. The first technique is called time tuning, or the paper title is Time Does Tell, Self-Supervised Time Tuning of Dense Image Representations. And we presented this at ICCV in 2023. All right. The main, all right. The main motivation is that we don't want to treat videos as a collection of frames, because this really misses the important stuff. If you see the bottom frames, you kind of maybe know what's going on, but if you look at the video, yeah, you know a bit more, right? Like it's similar to how a symphony is not really just a collection of notes. Yes, all the information is kind of there, but you're really missing the important stuff if you take this very sober look at it. And so what's missing is the passage of time, right? Like we know the frame rate, that's sort of trivial, but more than that, time really gives us the notion of object motion, object permanence, geometry, occlusion, as well as causality, that this caused that. This can only be learned via time, really, especially in the case of self-supervised signal. I mean, of course, you could make a labeled data set that says this caused that, etc., and have a huge amount of human labor put into that, and then maybe your model will eventually understand the training set, but it will struggle to generalize to a test set. All right, so how do we use time? How do we use videos in self-supervised learning? So the first place to look at is augmentations, right? So augmentations are the key technique in self-supervised learning these days. So in images, what people do is typically they augment the image typically twice and then say these two representations should be the same. Also called like different views. And then what the key principle behind this learning is that we have view invariance. And this might be okay for videos like this, where the first frame very much resembles the last frame. I mean, maybe the car now is not just in the shade, but slightly in the sun. But overall, you could say these two frames are, or overall, all the frames in the video are the same. But this generally doesn't make sense for all of the videos, right? So if you have a video that's like this, where the first frame is a car, and the last frame is really, really different from a car, it really doesn't make sense at all to say to the model, hey, put all of these frames into the same bucket and just do contrastive learning on it or anything like that. So we need to be a bit smarter than that and not force frame invariance here. And the solution is quite obvious, especially if you look at this transforming car. So instead of saying on the image level, these two should be the same, what we're going to do is we're going to do it in the spatially dense level. So what I mean is like when you push your image through your neural network, you get features for every patch. In the case of a transformer or in a ConvNet, you have spatially distributed features, right? And we're going to be using these features. So the features that correspond to, say, the number plate, they should be the same no matter which frame you look at. So we can say that these features should be the same. And similarly for the features of a bush in the background, for example. Now, in the case of self-supervised learning, of course, the difficulty is how do we know where did the number plate go? So which patch belongs to what other patch in the next frame? This is sort of the key question that in a way remains after this very, very obvious solution. And how do we go about this? We do this by tracking the image patches as a first step. So you can see the video at the top here. We're going to push it through a half frozen backbone. So in this case, we start off with a pre-trained DINO backbone. So in this case, we use an image trained model first and fine tune only the last 5 layers. We're going to be running self-supervised clustering on top of it using synchron knob. So we get prototypes and a cluster map here. And then we're going to be propagating these features across time. So for this propagation, we're going to be using all of the frames, all of the intermediate frames that we're going to be pushing through the visual encoder and simply propagating them across time, such that we know where did this patch go in the next frame, where did it go in the next frame, etc., until we reach all the way to the last frame. And then we have transformed our features across time, and then we can compare to where those clusters actually are. And this is a simple loss. So this is a cross-entropy loss that we apply here, where we cluster both at the beginning and at the end, and the beginning features get transformed according to the tracking module, or the feature forwarder, we call it. And then we simply say these two should be the same, because we know that, yeah, technically everything should have moved across forward with time. Now, in a bit more detail, since this is a tutorial, put in a slightly edited screenshot of the main code snippet, or the code is online. You can see that at the top, we have the synchron knob on the feature maps. So this is a get scores function. And then we iterate through the data. And in a way, it's not particularly difficult to understand. The make segmaps function simply does a mask propagation. And even that is nothing particularly novel. So if you look at, for example, DINO code, it already can propagate the mask from Davis datasets where you're given one foreground mask and you simply need to propagate it to the future. That's the same way we propagate our masks. And then simply there's some reshaping happening. And then at the very end, you see our loss, which is simply a temperature scaled hard cross entropy loss. So you can see it be the targets, they come from the last frame, and the P map, prototype map, comes from the first frame, I think here. And yeah, these two are compared, and then the loss is computed. So it's yeah, relatively straightforward. Does sounds more complicated than it actually is. So on the high level, there's multiple ways to use videos, right? So the first one I've mentioned already, the image-based one, where you simply use it as augmentations or as a data source, which is quite limiting. I didn't mention this other way that sort of is almost the elephant in the room, that you could use video architectures for using videos, right? That's of course one idea. You can use it as a data dimension. But in this work, what we're using time as is really as a signal here. So we have image-based encoders, and these image-based encoders obviously look at images, but the loss itself is governed by time. So the time dimension really only comes in at the loss stage. So there's no time embedding, there's nothing happening for the encoder. It's really just where we apply the loss here. And to make sure that time is really the key ingredient in our model, we first simply leave out the feature forwarder and simply assume nothing happens in the video. So that's assume static. And you can see that there's a huge difference in performance. If we actually model the video that something is happening versus just assume nothing happens, just static. Similarly, if we compare using a single frame to multiple frames, you can see that using a single frame, there's some performance because we start off with DINO, right? And there's some domain adaptation happening. If we start using 2 frames, that's already a gain. But once we start using 4 frames and 8 frames, you really see that the time signal is giving us some gains. And I think this makes it really clear that there's a lot of potential here in leveraging this temporal information. It's more than just learning invariances. It's about tracking and then seeing if you track, let's say, this hand, and then you see it rotate, then you get a really great natural augmentation. And you can use this for learning strong representations that, yeah, can, for example, even perform well on data sets like Pascal VOC. So in this case, we're evaluating on image-based data sets because we have image models. We train on videos and evaluate on images, which in this case makes for a really fair and easy comparison. Furthermore, the model can be, of course, used on videos itself. So on YouTube VOS and Davis, we can get really strong unsupervised video segmentation results. And also on Pascal VOC, we can get strong unsupervised image segmentation results or linear classifier. fully convolutional neural networks, so keeping the backbone frozen and training simply linear layers on top of it also really gives strong performances. Same here. In terms of qualitative results, it's also quite easy to spot that if you do this approach, and here we're simply running k-means on the frame-wise feature maps, you can see that time tuning gives quite crisp semantic segmentation maps. Similarly for this example, here I'm only showing time tuning examples, and here every video is over clustered into 5 clusters, so we're not counting how many objects there are and using that number, but instead always using k equals 5. All right, so for this paper, what's the source? The source in this paper was that first of all, videos do provide a very rich supervision signals. And as long as we don't use frame-wise invariance, but instead use patch-level invariance, we really get strong performance gains. And with that, we can improve upon the already strong DINO model, which was a key goal of this work. We've seen strongest improvements in unsupervised segmentation. And all of this work, all of this tuning only took a single GPU, and I think less than 2 days of training, even though we're using videos, and even though our final model outperforms DINO. So that's a potential of starting from a strong model that was trained on images, and then using video to really soak up this knowledge that's inside the temporal dimension. All right, next work I'm going to be talking about is called Is ImageNet Worth One Video? Learning strong image encoders from one long unlabeled video. Where the first author is Shashanka, who just presented. And this was a iClear oral and outstanding paper this year. And the starting point here was really that time tuning that I just presented you is great, fun, nice, but it used DINO as an initialization, right? And if I were going to tell you how great time is, it's really better to just say, let's ignore images completely. Let's just study the extreme case and try to see how good of an encoder can we learn by learning just from a single video and from scratch. So no ImageNet pre-training, no DINO pre-training, nothing whatsoever. Let's start from random initialization, and let's be even more extreme. Let's just take a single video. And another motivation is also that, I mean, babies also don't really look at ImageNet, as I hope I made clear by now. And babies actually develop a lot of visual abilities quite early on. So face recognition and color sensitivity already happens after three months. Depth perception, 5 months. Visual acuity, 6 months. So all of this is very, very quick. And again, they're not seeing all those fine-grained animals, dog breeds, and fish breeds that ImageNet has. So motivated by this, we thought, how can we get a data set that is natural, but also scalable? Because ultimately we're self-supervised people at heart. So how can we make a data set that can also scale? And we ended up with collecting videos of walking tours. Walking tours, you can type into YouTube, you can find millions of walking tours where people simply strap GoPros to their chest, walk around through cities, and record it. In this case, this is Venice. And our data set that we've collected, which has the most permissive license, contains 10 walking tour videos, which are 4K quality, so extremely high definition, usable for all kinds of purposes. You can use them for your startup, for your company, of course, academic research. We've open sourced everything. And if you find that these videos aren't enough, you can simply, put a GoPro on your dog or on yourself and collect more, right? That's a nice thing about this data set. It's very easy to collect more. It's very easy to collect more for your own personal use case, for your robot. If your house, your kitchen looks very different, all of this should apply. This data set itself has a couple of interesting properties compared to other video data sets. So, for example, if we simply wanna run a 20K object detector here across the number of frames across time, and we compare it to these other video data sets, we can see that actually there's a lot of objects happening, or a lot of objects in every frame. So on average, we see around 40 objects in our walking tour videos. And similarly, in terms of the long tail of objects, so what kind of rare objects happen, our walking tours have much more, a higher number of objects and much more of them as well. So it also makes sense, right? In a romantic movie, in this case, for example, the red line, what we're comparing, there's not much more than seeing faces and maybe a ring or two or whatever. But in the case of walking through a city like Venice, there's lots of stuff happening. There's cars, there's children, there's balls, there's boats, there's fishes, everything. All right. So this was the first contribution of the paper, so this new data set. And then alongside this, we also propose a new learning method, which we call DoRA, Discover and Track, or DoRA, for those that know, DoRA the Explorer. The high-level idea is the following, that we track multiple objects across time, and we're going to define what objects are in the self-supervised case here. And then we're going to enforce invariance of the features across time. So in a way, it's quite similar to what we talked about before. We're going to track in a way where the number plate did go, and then we're going to say, hey, it's still the same number plate, so put it the same. But we're not going to be doing this exactly on the patch level, but we're going to be accumulating these into what we call objects, which have sort of a higher granularity. All right, so how do we do this? So we have a video which contains these multiple frames. We turn them into patches because we're training VIT models. We're going to push them through an encoder, which is through the VIT model. Then we're going to have what we call multi-object tracker, which is really just the multi-headed self-attention inside the VIT, which I'm going to be going into more detail in the next few slides. But this yellow module, which will give us object masks for every frame. So basically, it will tell us this object is located here in this frame, located here in that frame, and located there in that last frame. And then we're going to be masking out everything else except for this particular object and pushing it through the encoder again. And then we're going to be saying, okay, now the representations, these two should be the same. So we're applying the DINO loss here, and we're going to be applying the DINO loss for multiple objects. So lastly, it doesn't just give us an object mask for one object, but multiple, right? So this loss is applied to multiple objects. So how does this multi-object tracker work in detail? I said already it's not a different component, it's not a differently trained model, but it's completely inside the VIT itself. So the VIT has a multi-headed self-attention, right? And so for this, we first obtain the query key and output Z embeddings at the last multi-headed self-attention block of the vision transformer. And from the multi-headed attention maps, we first draw a subset of K heads. So in this case, we're going to draw 3 heads. And these 3 heads, their objective is to discover the different objects from the first frame. And we're going to be using this attention map to pool the prototypes, to pool the query features into these objects features. And these objects, we call them prototypes, represent the features corresponding to the objects discovered by the different attention head. So each attention head is responsible for discovering its own object. And now we're going to be having this sync-on-knop mechanism, which refines these object prototypes to basically spread around their attention, such that not all attention heads are looking at the same object. And this improves the correspondence between the object prototypes and the patch embeddings. And then finally, we track these objects over the frames by using cross-attention with the patch key embeddings. And each mask clip can be considered sort of as a multi-object crop. And the crop plays a similar role to the crops in DINO, but it has a very arbitrary shape because of the attention mask and tracks an object over the video frames. And note here that, we're applying this to multiple objects. So our loss has multiple terms across all of the objects and across the frames. And at a higher level, if you didn't do this, if you simply looked at the attention across the different heads on the spatial features, you would have the problem that all the attention heads tend to look at the same object, right? So if you look at plain DINO, all of the attention heads more or less look at the subject, which is problematic if we want our model to be tracking multiple different objects. So the synchron knop optimal transport in a way enforces simply high entropy, that these heads look at different regions, but in a very soft way. So it doesn't enforce this in a very strong way that every head has a particular capacity or anything like that. But instead, it does this in a soft way, and it works pretty well. So we can visualize the attention of three heads with the colors red, green, and blue. So in this case, everywhere where the first head is looking, I will be coloring with the color red. Everywhere the second head is looking with blue, and the third head where that one's looking, it will be green. Now, if we don't apply synchron knop, you see these mixed colors. So if there's turquoise and yellow, that means more than one head is looking at it, right? Because it's not red, green, and blue. However, if we do apply our synchron knop measure, you can see that, first of all we see are these primary colors, red, green, and blue. And furthermore, you also see nicely that objects are being tracked. So the scooter is being tracked nicely, the building is being tracked, and that other car is being tracked. And this is exactly what came as the biggest surprise to us, is that multi-object tracking just emerges by training on a VIT with this loss. So yeah, you can see really the everything being tracked here, the human, the bicycle, the traffic light. And this is without any external tracker. This is without any external pixel level loss. This is just in a plain VIT, right? There's nothing else to the architecture. All right, but we came here to develop a new learning method, and a new learning method it is. So if we apply the DINO loss versus the DoRA loss, and apply that to video pre-training data from a movie, from Kinetics, Epic Kitchens, or on walking tours, we can see that DoRA generally is a much better learning method to train VITs on videos. Moreover, walking tours plus DoRA learning method is really a great match. So you can see really huge gains from applying DoRA on walking tours, which makes sense because we looked at walking tours dataset. It looked very dense. There's lots of stuff happening. So we knew a simple object-centric method such as DINO, which really focuses on one object, one frame, wouldn't do particularly well. And that's why we developed DoRA. So, and you can also see you can see that we're also measuring on ImageNet linear probe performance here. But more than that, how does it compare against, say, DINO trained on ImageNet? It looks as following. So here in blue, we have DINO trained on ImageNet, DoRA trained on a single walking tour video, or DoRA trained on 10 walking tour videos. And this is a ADE semantic segmentation benchmark where you do full fine-tuning. And we can see that already here, the DoRA trained with a single walking tour actually outperforms DINO trained on ImageNet. For CoCo object detection, we need 10 walking tours to outperform DINO trained on ImageNet, but still, we do outperform. And by the way, DINO, ImageNet, 1 million images, 10 walking tours is also roughly 1 million images. So really, in terms of data, blue and yellow are comparable. And we can see that across all the other data sets as well, that roughly speaking, DoRA trained on 1 walking tour is equivalent with DINO on ImageNet, and DoRA on 10 walking tours actually outperforms DINO trained on ImageNet nearly everywhere. So yeah, what's the source behind this paper? First of all, training strong encoders from scratch with a single video is entirely possible. And these models match DINO trained on ImageNet in terms of performance, and sometimes even outperform them. And the crucial component of this was the spatially dense training loss that leverages time. And we just used a single video, so imagine what kind of performance you could get if you used 1 million videos, and if you did this in a smart way. And scientifically interesting for us is that multi-object tracking emerges out of this training objective in a plain VIT. And lastly, walking tours are great for training vision models, as we saw, because they have these smooth transitions, there's no cuts, there's nothing suddenly happening. All right, that's it. That's the talk. So yeah, happy to answer any questions. Thanks.